Hi everybody, this is the Tobacco Auctioneer Test 1 review for Physics 2020. So this is an in-person only test, so please bring blank paper, pencil, and calculator. You can have a 3-inch by 5-inch index card as an equation sheet. I'm also going to go ahead and give you the constant sheet that's posted on our course webpage, as well as the back cover, the inside back cover of your textbook, Purcell and Warren, that has the cylindrical and spherical coordinates stuff on it. So you'll have that. This test is going to cover chapters 1 and 2 in Purcell and Warren through section 2.7. We're not covering this stuff on the differential forms. That'll be on the next test. So just through the integral stuff. So on to the material. So first of all, of course, charge is conserved and it's quantized. So no matter what charge you've got, you can write it as an integer multiple of the fundamental electronic charge, which is the charge on a proton or an electron. The magnitude of that charge is 1.602 times 10 to the minus 19 coulombs. Of course, protons have a positive charge and electrons have a negative charge in that amount. The coulomb is the SI unit of charge. But if you're working in CGS units, the unit for charge is the electrostatic unit, and 1 coulomb is 3 times 10 to the 9th ESU. Coulomb's law gives the force in between two charged particles. It has a similar form to the force between two masses, Newton's law of universal gravitation. However, the fundamental constant for the force between two charged particles, the Coulomb constant, is multiple orders of magnitude bigger than the gravitational constant, which makes gravity, of course, the weakest force. So here, K is the Coulomb constant, 8.99 times 10 to the 9th Newton meters squared per Coulomb squared. You can also write Coulomb constant as 1 over 4 pi epsilon naught, where epsilon naught is the permittivity of free space, which is equal to 8.854 times 10 to the minus 12 Coulomb squared per Newton meter squared. The magnitude of the Coulomb's law force is then K, Q1, Q2 over R squared. K is the constant. Q1 and Q2 are the charges of the first and second charges respectively, the magnitude of the charges, and R is the center-to-center distance between those charges. And of course, Coulomb's law gives the force between two point charges. And of course, in vector form, the force will point along the line that connects the two charges. And if they're like charges, then they repel one another. And so as shown in the diagram here, the force from 1 on 2 is pointing away from the other charge, as is F21. These obey Newton's third law, so action-reaction, they have the same magnitude, but of course they point in opposite directions. So the way that we define this is usually using spherical coordinates. So we have the r hat vector, which points radially away from, or points radially outward from each charge. And if you have multiple point charges, then you just sum up the force on one charge due to all the other forces. So if you have more than one force, you just do a vector sum. Remember, it's a vector sum of the forces, and it obeys what we call superposition. Now you can relate the potential energy to the force. The change in the potential energy moving through some force or field is equal to negative integral of F dot ds. Remember that the work is the integral of force dot ds, and remember that for conservative forces, the work done by the conservative force is equal to the negative change in potential energy, and that's where that negative sign comes from. Okay? Now, using this equation, you can derive the potential energy between two point charges, which we did last semester, actually, in Physics 2010. And that's K, Q1, Q2 over R, where R is the center-to-center distance between the charges, and Q1 and Q2 are the magnitude of the two charges, respectively. Okay? Of course, this shows that if the charges move infinitely far apart, that the potential energy between them goes to 0. If you have two charges that are the same sign, then the potential energy is positive and work has to be done to bring them together. If the two charges have opposite signs, then the potential energy is negative and work has to be done to keep the charges apart, because likes repel and opposites attract. And if there's more than two charges, then what you have to do to find the total potential energy is to sum over all pairs of charges, and that'll give you the total potential energy for the system. So for example, if you have 3 charges here, you'd have to find the potential energy between charge 1 and 2 between charge 1 and 3, and between charges 2 and 3, which is written out mathematically here down at the bottom. If you've got a lot of charges, then writing them out that way can get cumbersome and tedious, and so you can use this notation if you want to, where you do a double sum for j not equal to k, right? You're summing over j and k for k not equal to j, and then since that counts each pair of charges twice, you have to multiply by 1/2 out front. So that's what the 1/2 is for. But for your test, you'd probably just have a couple of charges anyway, and so doing it this way would be just fine. All right, electric fields. We say that there's an electric field that's established in the region of space around some kind of source charge. And then if you bring another charged object, like a little test charge, in the presence of this field, then you're going to get a force on that test charge. And the force can be written as F equals QE, where Q is the magnitude of your test charge and E is the electric field established by your source charge. Now, the direction of the electric field is pointing in the direction that the force would be on a positive test charge. If you've got a negative charge in the field, then the force would, of course, it would travel up the electric field line instead of down it. So, positive charges move parallel to electric field lines, negative charges move anti-parallel or up the electric field lines. Looked at this way, since the SI unit of force is the Newton and the SI unit of charge is the Coulomb, then the SI unit of the electric field would be the Newton per Coulomb. And as discussed later in a different equation, that's also equal to volts per meter. So, since we have the force between two positive charges, K Q1, Q2 over R squared R hat, or between two charges, I'm sorry, not just positive ones, then the electric field from a point charge could be written as KQ over R squared R hat. So electric field lines point radially away from positive charges and point charges and towards radially negative point charges. And of course, if you have a bunch of charges, then the electric field at a given point would be the vector sum of the electric fields due to each individual charge. We can represent electric field lines via vectors and in drawings. We show the arrow as pointing in the direction of the field, which is of course the direction that a positive charge would move in the presence of that field. We use the length of field lines and also the density of field lines to indicate the strength of the electric field in an area. And so since this electric field is diverging between A and B, you can see that the electric field density is larger at A than B, and that is depicted by having the lines closer together at A versus B. We talked about some special configurations and geometries for electric fields. It helps us develop an intuitive understanding of these things, which is useful for a lot of the ways that we use to find electric fields for continuous charge distributions later. So this is called a dipole when you have two oppositely charged particles that are separated by some small distance. That's a dipole. Here the positive charge is shown in red on the right and the negative charge on the left. And what happens is, since electric fields start on positive charges and end on negative charges, then you get this kind of configuration for the electric field for a dipole. Remember that we defined the dipole moment as P, which is equal to Q, the charge on one charge, times L, okay? L is the distance between the two charges, and the dipole moment points towards the positive charge, so it points from the negative to the positive charge. It's supposed to indicate, for example, the direction of the electric field as it leaves the positive charge of the dipole. Now, if you have, instead of a bunch of point charges, a continuous charge distribution, then one way to imagine that is to break your continuous charge distribution up into a bunch of little chunks, and then treat each chunk like a little point charge, and then find what the electric field is due to all the chunks. So if you do it that way, then since electric fields obey superposition, you would just do a sum over all your chunks, as is shown here. Now, if you have tiny little chunks, in other words, if the size of the chunk goes to 0, tends towards 0, then what you end up with instead is your summation becoming an integral. And so to find the electric field for a continuous charge distribution, you do K times the integral of dq over r squared r hat. Okay? Now, how would this play out in real life? Okay, how would this play out in real life? Well, first of all, what you would need to do is you would need to draw your distribution and divide it into little pieces, and then depict one of the little pieces on your sketch. So, for example, if we had a charged wire, which is shown here, this wire lies on the y-axis, and you're interested in what the electric field is at some distance x away from the center over here, you see on the right. Well, what you do is you draw a chunk, a single chunk, and you want to pick a chunk that doesn't have a high degree of symmetry. So, for example, you wouldn't want to pick a chunk at the origin because that would be misleading, okay? So you pick a chunk up here that's off axis, and you call that your little delta Q. And then you draw what the electric field line would look like from that little delta Q, and that's your delta E, okay? Now, what you're going to do is then write an expression for the electric field for that one little piece, that one little delta E. So you have different kinds of charge distributions. You've got linear charge distributions, surface charge distributions, and then volume charge distributions where it's more 3D. So this is 1D, 2D, and 3D. So you have to decide whether you've got a 1D, 2D, or 3D charge distribution, okay? And then you're going to write dq as either a line charge density times a little dl like you have here. So here if you have a dy, then it would be lambda dy, okay? Or if you had a surface charge density like a plane, then your dq would be sigma dA. Or if you have a volume charge density, a 3D thing, then your dq would be rho dV, okay? Once you've done all that, you're going to look at your expression for your dE, and you're going to see what's going to vary in that expression and what's going to stay constant. You're going to have to write the vector components of dE in each direction. Remember that the electric field is a vector, okay? So you can't just do k dq over r squared and call it a day. You can see here that this line has vector components. It has both x and y components. Now sometimes, like it will for this one or more of those components is going to sum to 0 when you do your full integral. So for example, if this is really the whole length and the origin here is in the middle, and this point here bisects the line charge, then you can see that from charges up above the x, the electric field would have downward pointing components, whereas below the x, the electric field would have upward. And then that would cancel out if you have a high degree of symmetry. And so that would mean that the y components of your electric field would sum to 0 as you do the whole line. So sometimes you can exploit symmetry in that way and thereby eliminate a little bit of work for yourself. Now, the x components in this bit, though, those are always going to point to the right at our position x here. So we're not going to be able to get rid of those. So what that means is that we have to solve for what our little delta E in the x direction is, and then integrate over delta EX from the limits to find the total electric field in the x direction. I hope that makes sense. And you might be using some trigonometry here to find the components. Then you're going to evaluate your integral to obtain your final expression and check your results. It's really easy to screw things up, so just double check and make sure that your answer makes sense. Are the units correct? Does the direction of the field make sense? Look at the extrema. What would happen as your point went to infinity? What would happen as your point shrank to 0? What would it look like? And then if it doesn't make sense from that aspect, then your answer is probably wrong. Okay, so that's a little sanity check kind of thing. Okay, now remember, we talked about dividing up your continuous charge distribution. You've got your little dq's, but you need to write your dq's in terms of a spatial coordinate because you don't want to integrate over charge. You want to integrate over space. And so remember that we do that with volume charge densities, surface charge densities, and linear charge densities. If you know that it's a constant charge density, and so, for example, it's 3 everywhere or something like that, then you can just take your total charge and then divide by either the total, volume, area, or length, depending on your geometry, to get your charge density, okay? So if it's a volume charge density, it would be the charge divided by the volume, and it would have units coulombs per meter cubed. If it's a surface charge density, then it would be the charge divided by the area, and would have units coulombs per meter squared. And if it's a linear charge density, then it would be a charge per unit length, and it would have units coulombs per meter. And then you would write your dq for volume, surface, and length elements respectively as rho dV, sigma dA, and lambda dL. Okay, so that's how that's handled. Now it's important to understand that if if you know that it's constant, then rho, sigma, and lambda might be some number. However, it doesn't have to be constant, and we worked some example problems where it wasn't. So make sure that you understand that rho, sigma, and lambda are actually functions if they want to be, okay, if you have a non-constant charge density. All right, so that's the direct integration technique for finding the electric field from continuous charge distributions. You want to do that technique when you don't have a high degree of symmetry. However, when you do have a high degree of symmetry for your charge distribution, you're going to want to use Gauss's law. So let's review Gauss's law, and the first step for that is defining the electric flux. The electric flux, which is often symbolized by the Greek letter phi here, and for electric flux I usually put a little e subscript. The electric flux is the product of the magnitude of the electric field and the surface area perpendicular to the field, okay? So that's written as the dot product of E and A, E dot A. The units of flux are newtons per coulomb, which is the unit of electric field, times meter squared, which is the SI unit of area. And as you can see here, what we do for surfaces is we define an area vector, okay? So here's the areas, and then here's the area vector A shown in blue. The area vector points perpendicular to the surface, so it points along the direction of the surface normal n hat, okay? And then the magnitude of the area vector should be the magnitude of the area. So it's whatever the area is times the surface normal, and that gives you your area vector. Now for open surfaces like these rectangles, the area vector could point in either direction. However, for closed surfaces like spheres, remember that your area vector is going to point radially outward, okay? So it's going to point outward from your surface, all right? And that's the definition for our area vectors. That's also shown here, okay? Our little dA at this point is pointing outward from the surface, so it's pointing away from the surface's enclosure, okay? All right, now, if you're looking at some closed surface, then the electric field might not point in the same direction along all points of the surface, right? So in that case, the flux is going to be the summation of the electric field at a specific point, here shown as point I for chunk I written here, right? The electric field at that point, dot product with the little differential area vector dAI, okay? Now, if your chunks become super small, this summation goes to an integral, and you're doing the integral over the closed surface of E dot dA. Now, the idea behind Gauss's law is that there's not going to be any net electric flux from a surface unless there's an enclosed charge, okay? So you have to have a charge enclosed by a surface to have a net electric field. Otherwise, what goes in comes out, okay? All right, now, Gauss's law states that the net electric flux is equal to the integral over the closed surface of E dot dA, and then that's going to equal to the net charge enclosed by that surface, the sum over all charges Qi, divided by epsilon naught. Now, if your charge is a continuous charge distribution and not just a bunch of little point charges, then that will equal to 1 over epsilon naught integral of rho dV, where rho is the volume charge density and dV is your little differential volume unit for your surface, okay? So, it's true that Gauss's law can be used to solve for any electric field for any charge configuration. But in practice, it's used as a shortcut, okay? If you're going to do a hard integral, in other words, if you're going to do something really tough, you may as well just go ahead and do the direct integration of k dq over r squared anyway, okay? But if you have a highly symmetric situation, then Gauss's law can get you out of doing some nasty integrals, and it's nice, okay? So it's used for highly symmetric situations mostly. So let's talk about the little Gaussian surface. You're going to try to choose a surface that satisfies one or more of these conditions. The value of the electric field can be argued from symmetry to be constant over the surface. The dot product of the electric field and the differential area vector can be expressed as a simple algebraic product. This happens when the field and the area vector are either parallel or perpendicular. That's when the little cosine theta term from the dot product is either 1 or 0 respectively. Okay, so you don't want your cosine of theta to vary between 0 and 1 over the surface. You want it to either be 0 or 1 everywhere, and that's it. Also, if the field is 0 over a portion of the surface, that helps too. Gauss's law says that in order to have a net field flux into or out of a closed surface, you have to have a source of charge inside that surface. And that source of charge causes the field to diverge, okay? So here's the deal. Let's say that you had a cylindrical surface symmetry, kind of like this depicted here, maybe a wire or something, okay? What would happen is that you choose a Gaussian surface that matches the symmetry of your actual surface. So for example, if the wire is this long blue arrow here, okay, and it's a charged wire, then you would choose a Gaussian surface that has a cylindrical symmetry, right? So you would choose a cylinder. Remember that your Gaussian surface is an imaginary construct. It's not a real surface. It doesn't have to coincide with your actual surface. It's just to help you visualize what's going on. Now, from this wire, the electric field would point up above the wire and down below it. It would point radially outward if you were looking kind of down the long axis of the wire, for example. And so your Gaussian surface here is going to have an area vector that is in the same direction of your electric field for the curved surface of the cylinder. For the end caps of the cylinder, the electric field is perpendicular to the area vector, and so that means that the cosine theta term will go to 0. So that makes this, since the symmetry matches, that gives that, you know, nice electric field, cosine of theta being 0 or 1 thing. Since I've chosen my cylinder to be concentric with my wire, in other words, the center, the long axis of my wire is the same as the center of my cylinder here, right? Then the electric field magnitude is going to be constant over the surface. Now the magnitude, not the direction. The direction changes as you walk all around. But the electric field magnitude is going to be the same all along the curved surface of my cylinder. Okay? So that's how the conditions are satisfied there. This means that you kind of have to have an intuitive understanding for what these electric field lines are going to look like for different charge distributions. You just have to know the way they point, though. You don't have to know the magnitudes. Okay, once you've done that, once you've chosen your Gaussian surface, the electric field should be constant over that surface. And so in your integral E dot dA, you're integrating over E dot dA, you should be able to pull the electric field out of the integral because it's constant over the surface. Your dot product should either be 0 or 1 for all surfaces, and then you just got E times the integral of dA. Now, if you know the surface area of common shapes, if you've got them memorized, then this is really easy. So, for example, the area of the curved surface of a cylinder is just the circumference of the cylinder, 2 pi r, times the length of the cylinder, L. So, boom, I know that, and then I can just write E times 2 pi RL is equal to the integral of E dot dA. It's super easy, okay? Now, does your Gaussian surface enclose charge? Okay, because remember that the integral of E dot dA is going to equal to Q enclosed over epsilon naught. So first, if your Gaussian surface encloses charge or not is a very important question. If it doesn't enclose any charge, then there's no electric field. 0, right? If it does enclose charge, does it enclose all the charge? If it does, then find the net charge enclosed and you don't have to do any integration. Okay, nice. If it encloses some but not all of the charge, then you're going to have to do your integration. Now, it's going to be either a line charge, a surface charge, or a volume charge. If the charge density is constant, then what you're doing basically is integrating, lambda dz, or sigma dA, or rho dV, right? If lambda, sigma, or rho is a constant, you can pull it out of the integral and you can just write down either the length, surface area, or volume of whatever you're doing for the result of that integral. The only time you're not going to be able to do that is if the charge density is not constant. Then you have to do the integral, okay? Okay, so now you should have an expression on the left-hand side and right-hand side. You set those equal and you solve for E, okay? Perform the same sanity checks. Are the units correct? Does it make sense? Okay? Now, bear in mind, this is a review of how to do Gauss's law. This is just a general quick review. Each one of the online lectures that I have posted and each one of the lectures that we have done is a deeper dive into this subject for specific geometries. I recommend that you understand and review all of those, okay? I'm not going to have time to do that here in my tobacco auctioneer review. All right, so that's how to find the electric field by direct integration of k dq over r squared or via Gauss's law. Okay, remember Gauss's law, high symmetry situations only. Don't even try to touch non-symmetric charge distributions with Gauss's law. Leaving that behind, let's now move on to the next topic, that we covered, which was electric potential. Okay? Electric potential, or voltage, is the potential energy per unit charge. And so we often write that the voltage experienced by a test charge in a field is the potential energy divided by the charge, U over Q. Okay? The voltage characterized just the field. Okay? Since the potential energy, delta U, was the integral of negative QE dot ds, when you find voltage, that's the integral of negative E dot ds, where ds is just some generic path that you're walking through when you walk through your electric field. So the voltage is independent of the charge, and that's why we did it, because it's a little annoying if you have a positive versus a negative charge to have to think about how the potential energy would change. You just want to think about what's going to happen with respect to the field and then apply that knowledge later to specific sign of charges. Also remember that potential differences or voltages and potential energies, the zero reference point is something to think about, okay? Oftentimes for point charges, for example, the reference point is set at R going to infinity, because remember the voltage for, or the potential energy for a pair of charges is K, Q1, Q2 over R. So if the charges are infinitely far apart, then that's potential energy of 0. So infinity is our 0 point. Now, when you get into circuits, that's not necessarily the case. You might force a 0 by connecting something to ground, and in that case, your potential at that point, your potential energy would be 0 right at the ground. You can also express the relationship in between the electric field and the voltage as a gradient. So the electric field is equal to the negative gradient of the voltage. So remember, the gradient operator is the partial with respect to xi hat plus the partial with respect to yj hat plus the partial with respect to zk hat in Cartesian coordinates. It's not quite that straightforward in the other coordinate systems. However, on the back cover of your textbook, I give you those relationships so you don't have to memorize them, okay? Okay, so let's talk about this. Let's say that we have an electric field pointing downward, as is shown here on this sketch on the right. The electric field is downward, so point B is at a lower voltage than point A. Remember, higher voltages are upstream in electric fields. Now, if you have a positive test charge moving from A to B, then that's the direction that the charge wants to go. Positive charges want to move downstream on electric field lines. Negative charges want to move upstream. So a negative charge would want to move from B to A, in other words. All right. Now, if you place the positive charge at A and let it go, there'll be a force on it that points in the direction of the electric field, and it would move it to B. What that would do is it would change the velocity of our charged particle if left alone. So it would increase, say for example, it starts off with no initial velocity at point A, its velocity would increase until it reached some finite value at point B. That would increase the kinetic energy. So if the kinetic energy increases, that means the potential energy decreases by the same amount because this is a conservative force, all right? Okay, now the electron would do something different. If it were, for example, an electron shot into a region with an electric field and it entered the electric field at point A with some initial velocity, then what would happen is there would be a force in the upward direction on that negative charge, and it would want to slow down, moving from A to B. So it would have a drop in the kinetic energy. Okay, so it would slow down, and then maybe at B, it even feels enough force so that it's completely come to a stop by B, and it wants to turn around and go the other way. In that case, its kinetic energy is converted into potential energy as it moves the way that it doesn't want to go with the field lines. So that's why we take out the charge when we talk about voltage and just discuss what's going on with the field. The potential and kinetic energy can go either way in an electric field depending on the sign of the charge, but the voltage is always going to be higher upstream in an electric field. For point charges, we can write the voltage as kq over r. This references a potential or a voltage of 0 at r equals to infinity. When you're infinitely far away from that point charge. Voltage obeys superposition, so if you have multiple point charges in a region and you want to know the voltage at some specific position, then you would sum up kq over r for each one of those charges, where r is the distance from the charge to the point in question, and q is the charge of the charge that you're at in the sum. Remember that if you have a continuous charge distribution, that you're going to integrate to find the voltage. So you would integrate rho dV, for example, to find the total charge. So what you would have is the voltage is equal to the integral of K rho dV over R for that continuous charge distribution. And we did this for an example of a sphere in class. All right. Another relationship that we discussed in class and had a homework question on was the potential energy stored in a field. So it turns out that fields are real things, okay? Originally it was debated as to whether or not an electric field was a real construct in and of itself or just something that you came up with to help describe the forces on charges in fields. But it turns out that Faraday was right and electric fields are real things. And what fields do is store energy. Okay, and so if you have an electric field E occupying some region of space with some volume V, then in order to find the potential energy stored in the field, you find epsilon naught over 2 times the integral of the magnitude of the electric field squared dV. Okay, and that would give you your potential energy. Okay, so that's a quick run through of the topics that we covered. Make sure to go back over the homeworks, work the practice tests. Remember that working problems is the best way to study physics. Let me know how that went if you're confused, and as always, I'll see you in class.